All right, so you see a wonderful and beautiful table here, which I will use to give you some tools that can help you to identify quickly what shear force function you will encounter and what moment function you will encounter depending on the load case. And the load cases that we discussed here are the concentrated force, the concentrated moments, the evenly distributed load, the very simple non-evenly distributed load case, which is linear. And then, of course, we're also going to look at no loads. And the way I want to do that is up here, I will put in what effect these will have in writing, and then I give you a representative diagram for that effect so that you have that as your reference. And we're going to do the same thing down here for the moment. And you can see that I already included the load cases as a symbolic representation. I invite you to do that too, so that we then can move on and start with the actual representation. Let's start with the concentrated force because that's where we started our lecture as well. Let's remember that the shear force diagram actually encounters a jump or a drop in the diagram. What do I mean by that? I mean that you, of course, have a rigid body, and that one has a jump right under the force at the same amount that the force actually produces. So the vertical component of that force actually leads to that jump or drop. And then this portion here is positive, and this portion here is negative. This, of course, could be the other way around. If your force, for example, is pushing up, then the jump would go from negative to positive. And likewise, this could also go from negative to more negative, right? So we understand that this just represents this jump here that we are trying to get across here, that this force causes a particular jump. Let me make clear that this is still the cutoff. And now we are ready to move on to the moment below, for which we've seen that we have an inflection point. Inflection point. Because we switch slopes from positive to negative. Sometimes it's from positive to lesser positive or from positive to more positive. It really doesn't matter. What ends up to be the case at all times is that you end up with an inflection point. And so if I want to symbolize that for this case here, let's just say that I have something that goes up here on the left side and then goes down on the right side. And of course, this could go in any direction, so I'm just going to symbolize it as such. And the important thing is to understand that this is a positive slope and this is a negative slope. And now I need to indicate that I cut this one as well. And that completes this diagram. Technically, we usually add these as well here, but it's not the point to say that we have a positive area and a negative area here. But it's important to state that we have a positive slope and a negative slope because of the relationship to the shear force. Now let's look at the next case, which the one that we discussed next in the class was really the evenly distributed load. And for that one, what we see in the shear force diagram is that we have a linear increase or decrease. And the way that looks like is the beam with the dashed fiber underneath now has a linear function acting somewhere randomly along the beam. And again, this is positive and then this is negative, but it could also be all negative and all positive. It doesn't really matter. What matters is that this slopes down from left to right. So this point here could also be beneath the beam, for example. Or this point, like all other ones, could be above the beam. It doesn't really matter. But generally, we understand that we have a linear behavior here. And what did we learn about that and how it relates to the moment? That we now have a parabolic moment function. So it's x squared, if you will, and the way I would draw this, of course, would be with a maximum under the shear force where it goes through 0. So maybe I should include that here so that there's a relationship between the two. And I could do the same right over here. Actually, let me indicate that this here is an inflection point. That's the most important part about it, but we are working on the evenly distributed load right now. So what we found is that we have a maximum somewhere along this line. And because we have positive values here and negative values here, we have a positive slope on this side and a negative slope on that side. So let's indicate that, and let's state that on the left side we must have a positive slope, whereas on the right side we must have a negative slope. And so this is positive slope, which then of course is parabolic. And I'm doing my best here to draw a parabolic function by hand. This is negative slope. And that is that. Of course, in reality, there is an area underneath it, but that's not the point of this diagram here. But just so that it looks complete, let's add that as well. All right, then the next one we talked about was the non-evenly distributed load case, where we actually end up with a parabolic function for the shear force, right? So here we add parabolic. And of course that means that here we look at cubic. We will talk about that in a second. Let's first complete the shear force diagram, which we said has to have, actually in this case, a slope of 0 here. And then it decreases and decreases and decreases and decreases more, even more, if you will, and even more. So it gets steeper and steeper. And so I can now connect these tangents. And in this case here we would look at positive and at negative. But again, the point is not to have positive and negative areas here under the graphs. That is not the point of this. The point is to understand that this entire system here, from here to here, could shift up and down completely. And you need to understand that it would then bend down with this shape here. Actually, I believe we can do much better than this, so let me try to make it prettier here so that it looks more like the function we would expect. All right, and of course now there's a relationship to the bending moment that is the same as always, which is where it's 0, we need to find a maximum, and we need to have a cubic function. So let's draw that cubic function, at least conceptually. And let's state that we actually have a positive maximum here, and we have a increase, another increase, and a lesser increase right there at 0, and then goes down. And so then I have a cubic function which looks something like this. And again, this happens to be positive, but the important thing is to understand that this here is positive slope and negative slope. All right, so those ones we have discussed in length as well, but we also touched upon some other ones, which is the one for the concentrated moments. So let's do that one first. So let's talk about the concentrated moments. What happens for the shear force diagram? You may remember this. We definitely have done it. It actually has no effect. No effect. That is important to understand. So I'm going to use this faint gray lines here to say that nothing happens here really. It's kind of amazing that you have a load case, but it has no effect on the shear force diagram. However, it has a very important impact on the bending moment diagram, and the bending moment diagram actually now has a jump or a drop in it. It is actually the same way that the concentrated force behaves relative to the shear force diagram. We now have a concentrated moment impacting the bending moment diagram. And so what you will find is actually that you have a clockwise or counterclockwise jump, And let's think about what that means. So this is turning counterclockwise, this is turning clockwise. If I now were to cut the system here and I come from the right side, so I release the entire system and bring in my internal force at that location, let's say this M here, so you can see that that would actually put the counterclockwise into balance. So the jump here, due to this force, would make it more positive because they are already acting against each other. However, if I cut the system here and then look at this portion of the system, so I move this purple arrow up to here and then look at only this part, then you see that they actually rotate together. So you would end up with a negative jump here. So symbolically, how that would look like would be with a jump that has the magnitude of the moment. And let's draw this one here. And then we have another one on the other side. But again, we need to understand from where to where we are jumping here. So this is positive. So you actually end up going from here to here. And I will symbolize that in a second. Whereas this one here would be negative. So that means you go from here to here. So I guess the best way to do that is by, for example, saying that, hey, I'm starting here and I'm giving myself an arrow here, and then I jump down, and then maybe I have something else going on here. Whereas on the other side, it's actually the opposite. I have a force that wants to, or a moment that turns it more positive, and therefore I'm going in this direction first, then I'm jumping up, and then I move on in this direction. So in this case, we would be looking at positive here, negative here, negative here. But different scenarios are different, and please don't get hung up on this if that kind of confuses you, like why it's up and down. I think it's enough if you remember that you have a jump in your moment diagram. That's the most important thing to understand here. All right, last but not least, we have the no load case, which you kind of already talked about, because that means that everything is zero there, and we can just draw that we have a shear force that could be zero, it could be positive, it could be negative. So let's just pretend that it's positive here in this case, and maybe just to be on the safe side so nobody sues me for wrong information, I will also draw another beam with the zero case, and then to be on the 100% safe side, I will also draw one with a negative shear force. And so this would look like this and like this. So we could have zero if there's really unloaded, but it could also be negative. Pretty much this is the case where in some of the previous lectures, the way I used to say that is by nothing happens, nothing happens, nothing happens, right? So because nothing happens, nothing happens, nothing happens, it stays constant, either constant positive, constant zero, or constant negative. So that should make sense. Why do I need to tell you this? You may think, that's already included here, but you need to understand that, of course, this has also an impact then on the actual bending moment, which could be, of course, also in three scenarios then in this case. So we could have the zero case, we could have the positive slope, and we could have the negative slope. And let's symbolize that so we can wrap up the information on this page. So I can have the zero case, which if I have zero shear force, you have zero bending as well. That's actually an important thing to understand. But if I have a positive shear force, I have a positive slope. So remember, that is the positive slope. And then for the negative case, I have the negative slope, which could be like this, for example. But this is also positive, this is also positive. And what we really need to understand is that we have a negative slope here and a positive slope. And that therefore shows us how these cases relate to each other, because remember, the very important thing that we learned before is that from the shear force to the moment we really integrate, or we actually took the derivative. to arrive at the shear force from the moment. But we also did this for the load case, so we could have done this integration here, or we could have taken the derivative in the other direction. But please keep in mind that when you integrate, so when you move from here to here or from here to here, that you always have to consider integration constants. Here's an example where you have actually integration constants. There are other examples which are beyond the purpose of this class. So just do not use integration blindly. It's always easier to do the derivative approach, but both of them work. But this completes now our table that you can see here on this page. It will give you a tool to understand which load case scenario leads to what shear force scenario and what bending moment scenario. This is all representative and symbolic, so please don't get hung up on the specifics, like for example that there's an inflection from positive to downwards. It could also be positive and then less positive and so on and so forth. But this should give you a good tool to help you when you're in question about a specific jump or behavior in one of your diagrams. So I hope this will help you to complete your homework and to actually analyze the upcoming example problems. So let's use this tool on one of the following pages and apply it to the upcoming problems that include actually evenly distributed load cases and non-evenly distributed load cases. So let's go ahead and start an example problem on the next page.